Welcome to the session Linear Partial Differential Equations of Higher Order with Constant Coefficients. A differential equation involving two or more independent variables and partial derivatives with respect to them is called a partial differential equation. A partial differential equation in which the partial derivatives occur only in the first degree and not multiplied together is called a linear partial differential equation. Otherwise, it is said to be non-linear. A relation between independent variables and the dependent variable containing arbitrary constants or functions from which a partial differential equation is formed is called a solution of the partial differential equation. Linear partial differential equations of higher order with constant coefficients may be divided into two categories as given below. First one, equations in which the partial derivatives occurring are all of the same order and the coefficients are constants. Such equations are called homogeneous linear partial differential equations with constant coefficients. Second one, equations in which the partial derivatives occurring are not of the same order and the coefficients are constants. Such equations are called non-homogeneous linear partial differential equations with constant coefficients. For example, dou square z divided by dou x square minus 5 into dou square z divided by dou x dou y plus 6 into dou square z divided by dou y square is equal to e raised to x plus y, and dou cube z by dou x cube minus 3 into dou cube z by dou x square dou y minus 4 into dou cube z by dou x dou y square plus 12 into dou cube z by dou y cube is equal to x plus 2y are equations of the first category. Dou square z by dou x square minus dou square z by dou x dou y plus dou z by dou x is equal to x square plus y square, and dou square z by dou x square minus dou square z by dou y square minus 3 into dou z by dou x plus 3 into dou z by dou y is equal to cos x plus 2y are equations of the second category. The standard form of a homogeneous linear partial differential equation of the nth order with constant coefficients is a0 into dou raised to nz by dou x raised to n plus a1 into dou raised to nz by dou x raised to n minus 1 dou y plus a2 into dou raised to nz by dou x raised to n minus 2 dou y square plus etc. plus an into dou raised to nz by dou y raised to n is equal to q of xy. Let it be equation number 1, where a1, a2, a3, etc. are constants. If we use the operators d and d prime for dou by dou x and dou by dou y respectively, we can symbolically write the equation 1 as a0 d raised to n plus a1 d raised to n minus 1 into d prime plus a2 into d raised to n minus 2 into d prime square plus etc. plus an into d prime raised to n of z is equal to q of xy, or f of d comma d prime of z is equal to q of xy. Let it be equation number 2, where f of d comma d prime is a homogeneous polynomial of the nth degree in d and d prime. The method of solving equation 2 is similar to that of solving ordinary linear differential equations with constant coefficients. The general solution of equation 2 is of the form z is equal to complementary function plus particular integral, where complementary function cf is the right hand side of the general solution of f of d comma d prime of z is equal to 0, and the particular integral pi is given by 1 by f of d comma d prime of q of xy. The complementary function. The complementary function of f of d comma d prime of z is equal to q of xy is the right hand side of the solution of f of d comma d prime of z is equal to 0. Let it be equation number 1. Assume that z is equal to phi of y plus mx, let it be equation number 2, is a solution of equation 1 where phi is an arbitrary function. Differentiating equation 2 partially with respect to x and then with respect to y, we have dz is equal to dou z by dou x, which is equal to m into phi dash of y plus mx. d square z is equal to dou square z by dou x square, which is equal to m square into phi double dash of y plus mx, etc. d raised to n of z is equal to dou raised to n z by dou x raised to n is equal to m raised to n into phi raised to n of y plus mx. Similarly, d prime raised to n of z is equal to dou raised to n z by dou y raised to n is equal to phi raised to n of y plus mx, and d raised to n minus r into d prime raised to r of z is equal to dou raised to n z by dou x raised to n minus r dou y raised to r, which is equal to m raised to n minus r into phi raised to n of y plus mx. Since equation 2 is a solution of equation 1, we have a0 into m raised to n plus a1 into m raised to n minus 1 plus a2 into m raised to n minus 2 plus etc. plus an of phi raised to n of y plus mx is equal to 0. Let it be equation number 3. Since phi is arbitrary, phi raised to n of y plus mx not equal to 0. Therefore, equation 3 reduces to a0 m raised to n plus a1 m raised to n minus 1 plus a2 m raised to n minus 2 plus etc. plus an is equal to 0, or f of m comma 1 is equal to 0. Let it be equation number 4. Thus, z is equal to phi of y plus mx will be a solution of equation 1 if m satisfies the algebraic equation 4, or m is a root of equation 4, which we get by replacing d by m and d prime by 1 in the equation f of d comma d prime of z is equal to 0 and dropping z from it. The equation f of m comma 1 is equal to 0 is called the auxiliary equation, which is an algebraic equation of the nth degree in m and hence will have n roots. Case 1. The roots are distinct, real or complex. Let m1, m2, etc. mn be the n roots. The solution of equation 1 corresponding to these roots are z is equal to phi 1 of y plus m1x, z is equal to phi 2 of y plus m2x, etc. z is equal to phi n of y plus mnx. The general solution of equation 1 is given by a linear combination of these solutions. That is, the general solution of equation 1 is given by z is equal to phi 1 of y plus m1x plus phi 2 of y plus m2x plus etc. plus phi n of y plus mnx. Case 2. Two roots are equal and others are distinct. Let m1, m1, m3, m4, etc. mn be the roots. Here f of m comma 1 is equal to a0 into m minus m1 the whole square into m minus m3 into etc. into m minus mn. Therefore, f of d comma d prime is equal to a0 into d minus m1 d prime whole square into d minus m3 d prime into etc. into d minus mn d prime. Hence, solution of equation 1 will be a combination of the solutions of the component equations d minus m1 d prime whole square z is equal to 0, d minus m3 d prime of z is equal to 0, etc., d minus mn d prime of z is equal to 0. Consider d minus mr d prime of z is equal to 0. That is, p minus mrq is equal to 0, which is a Lagrange's equation. The corresponding auxiliary equations are dx by 1 is equal to dy by minus mr is equal to dz by 0. Solving, we get y plus mrx is equal to a and z is equal to b. Therefore, the general solution of d minus mr d prime of z is equal to 0 is fr of y plus mrx comma z is equal to 0, or z is equal to phi r of y plus mrx. Now consider d minus m1 d prime whole square z is equal to 0. Let it be equation number 5. Let d minus m1 d prime of z is equal to u. Let it be equation number 6. Therefore, equation 5 becomes d minus m1 d prime of u is equal to 0. Let it be equation number 7. The solution of equation 7 is u is equal to phi 1 of y plus m1x. Using this value of u in equation 6, it becomes d minus m1 d prime of z is equal to phi 1 of y plus m1x, or p minus m1q is equal to phi 1 of y plus m1x. Let it be equation number 8, which is a Lagrange's equation. The auxiliary equations are dx by 1 is equal to dy by minus m1 is equal to dz by phi 1 of y plus m1x. Solving, we get y plus m1x is equal to a and z minus x into phi 1 of y plus m on x is equal to b. Therefore, the solution of equation 8 and hence equation 5 is f of y plus m on x comma z minus x into phi 1 of y plus m on x is equal to 0, or z minus x into phi 1 of y plus m on x is equal to phi 2 of y plus m on x, or z is equal to x into phi 1 of y plus m on x plus phi 2 of y plus m on x. Therefore, the general solution of equation 1 is z is equal to x into phi 1 of y plus m on x plus phi 2 of y plus m on x plus phi 3 of y plus m3x plus etc. plus phi n of y plus mn x. Hence, the complementary function of the solution of f of d comma d prime of z is equal to q of xy is x into phi 1 of y plus m on x plus phi 2 of y plus m on x plus phi 3 of y plus m3x plus etc. plus phi n of y plus mn x. Case 3. R of the roots are equal and others are distinct. Let m1 equal to m2 equal to m3 equal to etc. equal to mr. Proceeding as in case 2, we can show that the complementary function of the solution of f of d comma d prime of z is equal to q of xy is phi 1 of y plus m on x plus x into phi 2 of y plus m on x plus x square into phi 3 of y plus m on x plus etc. plus x raised to r minus 1 into phi r of y plus m on x plus phi r plus 1 of y plus m r plus 1 x plus etc. plus phi n of y plus mn x. The particular integral of the solution. As in the case of ordinary differential equations, there are formulas or methods for finding particular integrals pi of the solution of homogeneous and also non-homogeneous linear partial differential equations with constant coefficients. The formulas or methods are given below. Case 1. Q of xy is equal to e raised to ax plus by. Particular integral is equal to 1 by f of d comma d prime of e raised to ax plus by is equal to 1 by f of a comma b of e raised to ax plus by if f of a comma b not equal to 0. If f of a comma b is equal to 0, then d minus a by b d prime or its power will be a factor of f of d comma d prime. In this case, we factorize f of d comma d prime and proceed as in ordinary differential equations and use the following results. 1 by d minus a by b d prime of e raised to ax plus by is equal to x into e raised to ax plus by. 1 by d minus a by b d prime whole square of e raised to ax plus by is equal to x square divided by 2 factorial into e raised to ax plus by, etc. 1 by d minus a by b d prime all raised to r of e raised to ax plus by is equal to x raised to r divided by r factorial into e raised to ax plus by. The above results can be derived by using Lagrange's linear equation method. For example, let 1 by d minus a by b d prime of e raised to ax plus by is equal to z. That is, p minus a by b q is equal to e raised to ax plus by. The auxiliary equations are dx by 1 is equal to b into dy by minus a is equal to dz by e raised to ax plus by. The solutions of these equations are ax plus by is equal to c1 and z is equal to x into e raised to c1 or z is equal to e raised to ax plus by. Example. Consider the equation dou cube z by dou x cube minus 3 into dou cube z by dou x square dou y plus 4 into dou cube z by dou y cube is equal to e raised to x plus 2y. The symbolic form of this equation is d cube minus 3d square d prime plus 4d prime cube of z is equal to e raised to x plus 2y. Its auxiliary equation is m cube minus 3m square plus 4 is equal to 0 or m plus 1 into m square minus 4m plus 4 is equal to 0 or m plus 1 into m minus 2 whole square is equal to 0. Therefore, m is equal to minus 1 comma 2 comma 2 and the complementary function is Cf is equal to x into phi 1 of y plus 2x plus phi 2 of y plus 2x plus phi 3 of y minus x. The particular integral is pi is equal to 1 by d cube minus 3d square d prime plus 4d prime cube of e raised to x plus 2y, which is equal to 1 by 1 cube minus 3 into 1 square into 2 plus 4 into 2 cube into e raised to x plus 2y. Putting d is equal to 1 and d prime is equal to 2, which is equal to 1 by 27 into e raised to x plus 2y. Therefore, the complete solution is z is equal to x into phi 1 of y plus 2x plus phi 2 of y plus 2x plus phi 3 of y minus x plus 1 by 27 into e raised to x plus 2y. Case 2. Q of xy is equal to sin ax plus by or cos ax plus by. Particular integral is equal to 1 by f of d square comma d into d prime comma d prime square of sin ax plus by, which is equal to 1 by f of minus a square comma minus ab comma minus b square of sin ax plus by, provided f of minus a square comma minus ab comma minus b square not equal to 0. If f of minus a square comma minus ab comma minus b square is equal to 0, then d square minus a square by b square into d prime square will be a factor of f of d square comma d into d prime square. In this case, we proceed as in ordinary differential equations and use the results 1 by d square minus a square by b square d prime square of sin ax plus b is equal to minus x by 2a into cos ax plus by, and 1 by d square minus a square by b square d prime square of cos ax plus b is equal to x by 2a into sin ax plus by. Example. Consider the equation dou square z by dou x square minus dou square z by dou x dou y is equal to sin x into cos 2y. This can be written in symbolic form as d square minus d prime of z is equal to sin x into cos 2y. Its auxiliary equation is m square minus m is equal to 0 or m into m minus 1 is equal to 0. Therefore, m is equal to 0, 1 and the complementary function is cf is equal to phi 1 of y plus phi 2 of y plus x. The particular integral is pi is equal to 1 by d square minus d into d prime of sin x into cos 2y, which is equal to 1 by d square minus d into d prime of 1 by 2 into 2 sin x cos 2y, which is equal to 1 by 2 into 1 by d square minus d into d prime of sin x plus 2y plus sin x minus 2y, which is equal to 1 by 2 into 1 by d square minus d into d prime of sin x plus 2y plus 1 by d square minus d into d prime of sin x minus 2y, which is equal to 1 by 2 into 1 by minus 1 square minus minus 12 into sin x plus 2y plus 1 by minus 1 square minus minus 1 into minus 2 sin x minus 2y, which is equal to 1 by 2 into sin x plus 2y minus 1 by 6 into sin x minus 2y. Therefore, the complete solution is z is equal to phi 1 of y plus phi 2 of y plus x plus 1 by 2 into sin x plus 2y minus 1 by 6 into sin x minus 2y. Case 3. Q of xy is equal to x raised to m into y raised to n. Particular integral is equal to 1 by f of d comma d prime of x raised to m into y raised to n, which is equal to f of d comma d prime the whole raised to minus 1 of x raised to m y raised to n, where f of d comma d prime the whole raised to minus 1 is to be expanded in series of powers of d or d prime and operate on x raised to m into y raised to n term by term. Example. Consider the partial differential equation dou square z by dou x square plus 3 into dou square z by dou x dou y plus 2 into dou square z by dou y square is equal to x plus y. This equation may be written as d square plus 3 into d prime plus 2 into d prime square of z is equal to x plus y. Its auxiliary equation is m square plus 3m plus 2 is equal to 0 or m plus 1 into m plus 2 is equal to 0, which implies m is equal to minus 1 comma minus 2. The complementary function is cf is equal to phi 1 of y minus x plus phi 2 of y minus 2x. The particular integral is pi is equal to 1 by d square plus 3 into d prime plus 2 into d prime square of x plus y, which is equal to 1 divided by d square into 1 plus 3 into d prime by d plus 2 into d prime square by d square of x plus y, which is equal to 1 by d square into 1 plus 3 d prime by d plus 2 into d prime square by d square, the whole raised to minus 1 of x plus y, which is equal to 1 by d square into 1 minus 3 d prime by d plus etc. of x plus y, which is equal to 1 by d square of x plus y minus 3 by d of 1 is equal to 1 by d square of y minus 2x, which is equal to 1 by d of yx minus x square, which is equal to y into x square by 2 minus x cube by 3. Hence, the complete solution is z is equal to phi 1 of y minus x plus phi 2 of y minus 2x plus x square y by 2 minus x cube by 3. Case 4. Q of xy is any function of x and y. Particular integral is equal to 1 by f of d comma d prime of q of xy. Resolve 1 by f of d comma d prime into partial fractions considering f of d comma d prime as a function of d and operate the following: 1 by d minus m d prime of q of xy is equal to integral q of x comma c minus mx dx, where c is replaced by y plus mx after integration. Example: consider the equation dou square z by dou x square plus dou square z by dou x dou y minus 6 into dou square z by dou y square is equal to y into cos x to solve. This may be written in symbolic form as d square plus d into d prime minus 6 into d prime square of z is equal to y into cos x. Its auxiliary equation is m square plus m minus 6 is equal to 0, which implies m is equal to minus 3 comma 2. The complementary function is Cf is equal to phi 1 of y minus 3x plus phi 2 of y plus 2x. The particular integral is Pi is equal to 1 by d square plus d into d prime minus 6 into d prime square of y cos x. That is equal to 1 by d plus 3d prime into d minus 2d prime of y cos x. That is equal to 1 by d plus 3d prime into 1 by d minus 2d prime of y cos x, that is equal to 1 by d plus 3d prime integral c minus 2x cos x dx, where c is to be replaced by y plus mx is equal to y plus 2x after integration. That is equal to 1 by d plus 3d into c minus 2x into sin x minus integral of minus 2 sin x dx, which is equal to 1 by d plus 3d prime of y plus 2x minus 2x into sin x minus 2 into cos x, that is equal to 1 by d plus 3d prime of y sin x minus 2 cos x, which is equal to integral c plus 3x sin x minus 2 cos x dx, where c is to be replaced by y plus mx is equal to y minus 3x after integration, that is equal to c plus 3x into minus cos x minus integral of 3 into minus cos x dx minus 2 sin x, that is equal to y minus 3x plus 3x into minus cos x plus 3 sin x minus 2 sin x, that is equal to minus y cos x plus sin x. Therefore, the complete solution is z is equal to phi 1 of y minus 3x plus phi 2 of y plus 2x minus y cos x plus sin x. Non-homogeneous linear equations. If f of d comma d prime is not homogeneous in the equation f of d comma d prime of z is equal to q of xy, then it is called non-homogeneous linear partial differential equation. Its complete solution is equal to complementary function plus particular integral. To find complementary function, factorize f of d comma d prime into the form d minus a into d prime minus b. Then d minus a into d prime minus b of z is equal to 0, which implies p minus aq is equal to bz. The auxiliary equations are dx by 1 is equal to dy by minus a is equal to dz by bz. Therefore, dx by 1 is equal to dy by minus a implies dy is equal to minus a dx, which implies y plus ax is equal to c. Also, dx by 1 is equal to dz by bz implies dz by z is equal to b dx, which implies z is equal to d into e raised to bx. Therefore, z is equal to e raised to bx into phi of y plus ax. Hence, the complementary function is the addition of the solutions to the various factors. The methods to find particular integral are the same as those for homogeneous linear equations. Example: consider the equation d square minus d prime minus 2d of z is equal to cos 3x plus 2y. Here, f of d comma d prime is equal to d square minus d into d prime minus 2d, which is equal to d into d minus d prime minus 2. The solution corresponding to the factor d minus d prime minus 2 is e raised to 2x into phi of y plus x. Therefore, complementary function is equal to phi 1 of y plus e raised to 2x into phi 2 of y plus x. The particular integral is pi is equal to minus 1 by 15 into cos 3x plus 2y plus 2 sin 3x plus 2y. Hence, the complete solution is z is equal to phi 1 of y plus e raised to 2x into phi 2 of y plus x minus 1 by 15 into cos 3x plus 2y plus 2 sin 3x plus 2y. Let me conclude this session. In this session, we have discussed the methods of finding solution of a homogeneous linear partial differential equation with constant coefficients. The methods are similar to ordinary linear differential equations with constant coefficients. The general solution is of the form z is equal to complementary function plus particular integral, where complementary function depends on the nature of roots of the auxiliary equation and the particular integral depends on the right-hand side function of the given equation. We discussed 3 cases of finding the complementary function and 4 cases of finding the particular integrals. Also, we have discussed the method of solving a non-homogeneous linear partial differential equation. Now, you may try to solve the following partial differential equations. First one, d raised to 4 minus 2 into d square d prime square plus d prime raised to 4 of z is equal to e raised to x plus 2y. Second one, d square minus 2 into d prime plus d prime square of z is equal to 2 cos y. Third one, dou square z by dou x square minus 2 into dou square z by dou x dou y plus d prime raised to 4 is equal to sin x into cos 2y. Fourth one, d cube minus 7 into d prime square minus 6 d prime cube of z is equal to x square plus xy square plus y cube. Fifth one, d square minus d prime plus d prime minus 1 of z is equal to e raised to 2x plus 3y plus cos square x plus 2y. Let me suggest a few books for your further reference. First one, An Elementary Course in Partial Differential Equations, 2nd edition by T. Amarnath, Narosa Publishing House, New Delhi, 2003. Second one, Ordinary and Partial Differential Equations by M.D. Raisingania, Sultan Chand, New Delhi, 2010. Third one, Differential Equations and Their Applications, 2nd edition by Zafar Hassan, Prentice Hall, New Delhi, 2006. Fourth one, Partial Differential Equations and Integral Transforms by T. Veerarajan, Tata McGraw-Hill, New Delhi, 2004. Fifth one, Advanced Engineering Mathematics by E. Kreisig, John Wiley and Sons, New York, 1999. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.